can use this as a good illustration. You don't probably need a table. Well, what else you can put in this table? Distance?
Table would be,
Distance.
well, I have another plot for bond distance too. Not super helpful.
Right, but my point is, if you're creating a table, right, then you can put, like, sometimes it's hard to really get, depends on your scale, right? But sometimes it's really hard to get the exact numbers just looking on the figure, especially if it's so sparse or whatever, sparse, whatever, right? So that's why you can have a figure, but you can also have a table, and people are really interested to see exactly the value, right? Here you probably can figure it out, but when you have many of them, like what exactly is the difference between this black and blue or whatever then table, it can be not only figures, or even in the main text, but just as a table. But then, so this would be your name of the complexes, this would be your numbering as you use, right? And then, for example, here would be dipole, and you can order them in the same way as you ordered in this one. Then you can put the bond carbon nanotube, I don't know, let's call it R group, right? Distance bond. This is the distance which just between.
Tube to defect. Carbon on the tube, carbon, first carbon.
Right.
Or first.
So you walked off.
Yeah. And they're all attached to the carbon.
All the old ones.
And for name, I would suggest you use, because we have two guys versus one guy is this and one is hydrogen. So we probably can use this kind of as notation. So you can start with H3H, right? And so one time you go to H3.
If you're running the email,
In the past, I've used
to
underscores instead of slashes. Do you prefer
on
slashes?
my account always.
No, here it should be the real name of your. Oh, you mean?
Well, I abbreviate.
Oh, so you have the whole group.
The whole group underscore in the second.
No, I think slash would be.
Okay.
I don't know. Because underscore looks like a bond. Okay, I know in physics, I'm not thinking about bonds. They will be not missing it. I mean, not really interpreting it. But in chemistry, this sign might be considered as a bond or something. And technically they're not bonded.
And you need to project.
So they're not bonded with each other. So they bonded to the nanotube. Okay, so I would suggest put a slash, but then consistently, right? So you use these notations all over. And then you can, and actually this table, and maybe graphical representation, or maybe this table would be good enough, where you go in with your 1, 2, and so on, right? Notations up to 12. And then, yeah, in all other figures, you can really use, instead of large kind of these notations, you can just use the numbers, which is definitely much easier for notations. But we need to, but we need to be really consistent and be careful, because especially if we switch in some of these groups, right, and you forget to switch the numbers, then you talk about one thing and you show in actually the other thing. So okay, dipole moment, bond distance, band gap, right? What else? Splitting between. We probably don't need splitting band gap, right? So which is band gap of 16 minus band gap of
So you can.
defect, right? This is what we call WG. What else? And the splitting, the excitation splitting. Right? I guess this is the main important information which we need so far. Anything else? But this has to be fixed in whatever your methodology. So you use which functional?
Can't be
Calculated by Canvas 3D.
630 defect atoms.
And then, so it's STO3G, yes? For carbon nanotube? For all the whole group, right? For the defect group. Are we waiting for people or what?
It depends how you define people.
For extra people.
Oh.
Chemical structural features,
Did they confirm that they come? Because if they don't confirm, we don't need to wait. If they are going to come, then we can wait for them. but I mean, like, be sure that you're not like in this figure, right? If you have it,
In the final draft, I'll make sure that it.
yeah, if you're using a mixture here, not a good thing. So this table, and for some, and probably we will go with this table to the main text, right? Table 1, because it gives you need it
It'll be a
mainly
long
for the
table.
12 lines.
Well, so the dipoles aren't the same necessarily for every.
Oh, sure. We also have different types of configurations, right? Because each of them will have in this O plus, and so on. So we kind of have one, but this, yeah. So it's will be one table, one table, 12 times.
Whom do we need?
5, 6, 7.
Whom
7?
do we need?
Ewan?
Ewan, Aaron, Daniel, Alyssa?
Yeah, she usually comes 1 hour later.
Anyone else? London?
I guess he also comes later. I think they come after 5. Usually on Friday, right? Did they mention?
Do we need anyone else?
Actually, Alyssa should not. Alyssa says that she can come before me. She forgot. 6. So we have actually 12 times 6. Yeah. So we have 60, 72.
Where do you 12?
12 compounds. No, not 12. Like, I thought each of them.
This is dipole. Magnitude of the one
Then I'm completely confused. So it's actual value.
Yes.
Wow. So it really varies from 1 to 12 device?
It's total system.
Almost to order magnitude. So it's really significantly changing. 10 times more, right?
Yeah, that's why I wanted to show you this plot because we never.
Oh, okay. I kind of, then I'm confused.
Yeah,
Because I thought you just, that's the same, right?
Yeah.
What's the difference?
No.
Oh,
Oh, this is absorption. This
And
is
this is-
bank. And this is all.
and how many different confirmations you have? Then you probably, but I was kind of, oh, and now I understand, yes. But I was, because each of these, but still, well, yeah, and then we have even more than 12,
Yeah,
right?
it's quite a bit more.
Yeah, so then probably, we can go with this one.
The table will be more than 100 rows. I'm sure.
Well, yes, we can definitely put it in a. Yeah, then we probably can introduce this notation somewhere because you need some illustration of your structure, right? Somehow, and we can. I don't remember what because I remember we were discussing for your poster, right? And you were doing something, but I still was not very happy with your thing. I mean, you can do better than this. I mean, just a little bit more aesthetically better. Right? So it will be more clear figure and all information will be there. So maybe we need to discuss first with your, or you can create by yourself and then we can modify it slightly. Kind of an analogy what you were trying to do in your, because your first figure has to be structure. So people understand what's going on there, right? Because, so they can have some image behind their eyes so they can then kind of relate it to here. And then we can use this, because I was thinking you really kind of just mark them as 1, 2, 3, 4 and so on. But you, instead of all refer to these names, right? You can really mark it as 1, 2, 3, 4, and then it would be 1 O plus, 1 O plus plus, 1P or 2P, 3P, and so on, right? So much easier rather than real actual names. But then we have to be really clear with this nomenclature. I mean, put it once and then fix it all over all figures, all discussions and so on. So I would say you need then to create, and then in the table it also will give this, but you're right, this table probably will go to, so it's S table 1, right? So it goes to supplemental just because it's too long. And I'm kind of thinking, and do you really have data, the same exactly data for all of them are available with this when you have just STO basis as well? You do?
Say again. Question was-
Like this table will include information on dipole moments, bond
Oh.
distance,
I
difference in the ground state band gaps, right? E11 and defected one, and difference in excited states between the defected ones and pristine one, right?
I could get everything for STO.
I would, because it goes to supplemental, I would suggest like you put in your whatever it is, for example, 1 dB, like this is typing device, 1 dB, and you can put parentheses, just making it up. Parentheses would stay for pure STO3G basis. Make sense? So then you can easily, in this big long table, we can easily see some of them will be very close, probably. Some of them maybe will see bigger difference, especially with fluorines, right? And with the slow alkyls, looks like this base is definitely not working anymore, right? But this is goes to supplemental. It's not very main ideas, but in this and same here, right? Because bond distances might be different, your gaps will be slightly different, maybe not slightly, and these ones will be different. So then you just create, because this will be really combining all information from all your figures into the table, which is still easy to follow, right? It's just long. This is all the problem. That's why we cannot. Hey, you're appearing good. That's why we put it in supplemental, but it probably will be easy for you as well, so we can compare all these guys just across. So it's okay to compare the first page, but the other ones, if you print them, it's okay. But looks like you really need this table for yourself. There. And then for naming, I still suggest that you create your structure. You don't say which figures.
I haven't included either.
Huh? So you create.
Java, do not worry, even if not many people come, it will be recorded, you can share it.
Yeah, you probably will be.
No, I'm
like
just
more than
waiting.
just-
No, I'm just waiting to get it
No,
done.
we actually done. We're just waiting for them, but now they're here. And think about.
My hope is gonna be short meeting, so
If you done, we can.
No, that's what we all say, Javed. That's what we all say.
Changes.
Okay.
Did you take a look at it?
Yes, we will do one more
So this is still-
last, probably last
this is your
iteration
Yeah.
to
For
take
this
care
one. So
of
they all
the
together.
intermission
They'll connect.
breaks.
Okay.
Because right now they're kind of random,
Yeah.
and people who come from different sessions, they need to be trained, so if they jump between sessions, they come to middle of the session at the same time.
Okay.
The disorder may.
Oh, in the first version, we were trying to put, especially in the mornings, right, 40, 30, 30.
Uh-huh.
And I think in the evenings, we also were maybe 30, 30, 30, 30, like 2 hours or
Yeah.
something, or around it. But now they're all kind of mixed.
So, okay, thank you guys for coming. And so I'm going to talk about the just only result on small part of my one project and silver project. So this is kind of, I will show you only result part. So no other discussions, or introduction parts. But before going to result, and just a few things about why we are interested about electrochemical properties, especially reduction potential of the small silver cluster. So this is important because silver cluster is reported for a lot of different purpose. One purpose is like for oxidation catalysis, like by oxidation, using their oxidation potential is catalyzed to or introduce some other reactions, those kind of things. It's also reduction potential also important to define the growth rate or silver cluster growth mechanisms, because there were several reports and they discuss about several things. Several where they say that dependence on the oxidation state can change their photophysical properties, also their growth charge cluster. So especially, so in overall, the reaction potential is important things to describe the synthesis procedure as also their photophysical properties and everything. And also, we also found out that structural geometry conformation of the silver cluster also depends on their oxidation state. So if you want to know the structure of the conformation, it's very important to define the from the point of view of the reduction potential. So that's why we considered like very small silver cluster from the 4 to silver 10, but it's a lot of data. So in main paper, I have a plan to include all data, most of the data in this as supplementary information. And here I'll show you most of the information for 5 and 6 is kind of representing the information of this one. No, this is not that. Oh, okay.
So in the bare structures, this is also optimized structures, right?
Yeah, this bare structure is optimized one, my case, yeah.
And you start your initial structures based on the published in literature, right? So you don't just make it up by yourself.
Yeah. So in this is in the reported literature, we saw that they report the silver cluster and silver 5 as a planar geometry, the trapezoid geometry and triangular planar. Those are lowest energy geometry. So what we did for starting as the initial geometry, we took that geometry and precipitated each silver atom by cytosine. That means ligands and silver atom ratio is 1:1 in all considered conformations, and then I optimized it. And for bare one, in this case, these ones are same as reported ones, and this is because of its neutral one. All other, I just put the charge and then optimize this one.
And other reports on a bare charged
They reported only 1+ charges.
1+?
Yeah.
But you do have 1.
I do have 1+, and I do have it in addition
But
to
do they
1-
coincide
and 2+.
with what was reported
Yeah.
or not? So like
Yeah,
those structures
this
with
one is
plus,
coincide with the reported one is pretty one.
so and again, you just start with this geometry in the neutral case, put the plus charge,
And then
optimize, and you
it.
get in pretty much the same as was already.
Same as here.
But the position of ligands is also random.
Sorry.
The position of, like the geometry of the ligand.
No, it's not
In
linear,
initial
because you can
geometry,
see one.
initial geometry it was ordered. In each silver, I just coordinate with one ligand. So there have no other randomness. This randomness arises after optimizations here. So in initial geometry for 6, suppose like 6, I put the 6 cytosine into with this coordinated with 6 silver, and then
And again, your all the structures are optimized. It's not your initial. It's
no, this is
after
optimized
optimization.
one. All are optimized structure
So
here.
like you can see that this ligated silver 6, it's pretty much consistent with what you kind of expect. But with the charges, then yeah, they doing some
There is
strange
something.
things.
An important thing is for the almost all computational calculations, they included they talk about the bare silver cluster, or they put very limited ligand like one ligand like cytosines or one guanides. But they're saying that in almost they have a very common report is saying that in less than 6, their 6 or smaller than 6 cluster is always planar, and when you increase the charge in the 6 or you're going to beyond the 6, I mean larger size than 6, then they started to form 3D configured like banded or cluster size. But when I precipitated by cytosine, if you look on the first one, it seems like it's planar, but is optimized one is not actually planar. They form the bow tie shape, is called, but in my case it's like twisted bow tie shape. So this name actually taken from the literature, but when I put the 1+, this kind of planar, and other two, it's also become twisted, and also silver 6 is also twisted, and in vacuum is neutral one, it's also planar, but if I do this calculation in the water, it also gives us a like 3D shape. So one important thing is when we do your computational study with this cluster, is important to including the precipitation, because it can change their geometry, and also
Yeah, but
have
so
superparts
because
too.
we doing this work for the paper, right?
Yeah.
As a draft, and so you have do you have a figure? Maybe it goes to supplemental, pretty much the same figure but optimized in a solvent.
And I didn't include the solvent one because in this calculation almost we all talking about everything in the vacuum system. So that
Are we? I think we do have solvent. You actually
We have-
calculate your reduction potential vacuum results minus solvent, right?
yeah, but that one is geometry get from the vacuum, and then
Also, you not optimize geometry in a
no,
solvent.
it's just for solvation energy. For solvation
I
energy,
see.
we optimize in geometry vacuum, and then put the solvent, and then get the solvation energy.
Okay, but again, if some asks, like for example, these guys has to be in a solvent, right? They should have a significant effect. since we don't optimize in solvents, and what would be the reason why we don't?
And I would say it's kind of to analyze the structural fit or getting overall result rather than getting a real scenario. We wanted to see how it's changing with the precipitations and so on. So
But
reaction
your
potential
change
also
might be
changing.
significantly different in a solvent, and whatever your conclusions will be in a vacuum might be not coincide with a solvent in this case, right?
I would say yeah, maybe it's going to be a big story,
Well, I would say-
story with the solvent then.
I would say maybe you can find a different reason. You can probably say that because we have, like, for bare silver clusters, solvent effect is maybe really significantly changing the geometry, the properties, electronic optical properties. But for the for these guys, they're because you have all silver is kind of encapsulated into the bulky DNA bases, right? And they kind of protect at least silver atoms from direct interaction with a polar environment, right? Probably we expect that solvent in this case should not significantly affect the overall structure and electronic properties. If you have ligands on the surface, they kind of screen out this solvent effect. I mean, again, just as
yeah.
explanation, maybe it's not,
Mhm.
we understand it's probably, still if you do optimization in a solvent, there might be big differences. But do we have
Yeah.
at least one or two structures optimized in a solvent, right? We do.
We have all the structure and optimus in solvent, yeah, but not included in this paper yet.
Uh,
Yeah. In another paper, we almost wrote a
But
draft.
are the
that-
structures very different in a solvent?
in case of the silver, core cluster is not that much difference,
For neutral
but
one?
core means only silver core shape and things, yeah. But they have a noticeable difference in case of 6 in neutral is because of ligands. Because if you look at here, this ligand, this initial geometry, this ligand was in parallel position, but after optimization is going flat and they form a like network type things here. So, but in solvent, they don't form this kind of uniform network here.
Oh, so you have like hydrogen bond formation between ligands, between bases?
In vacuum,
fact.
yeah, in vacuum.
And in solvent, of course, you screen out this.
Mm-hmm.
So they're not affecting very much the silver atoms probably, but they're affecting stronger the alignment of bases then, okay?
Yeah, and it's also changed the photophysical properties. I mean absorption properties significantly. Yeah,
Mm.
and I have that discussion in that
Next
paper.
time.
Yeah, a solvent and vacuum comparison. So from the structural point of view and another thing is it changes the planar symmetry on the higher charges like 2+ charges because of their 1+ and 1- and 2+ is given as another special type of conformations. Is kind of similar to the subcluster formations. There was some experimental report and other report. The silver cluster also can form by forming a subcluster. Subcluster means if you look on here, these are 6 silver, they form the 2, 2, 2, and another report they also form like 3, 3 silver. So you will get this kind of conformations here. And so from this one, the main conclusion point is actually for transformation of the 2D to 3D conformations can be possible in presence of ligands. Because of their ligand interactions, it's changed their conformations. So planar geometry is not a common in that case, so we included this one. And the next figure is about the actual reduction potential. So before going reduction potential, I just very briefly showing you how I calculate the reduction potential. So there is a name of this cycle, I forget the exact name of this cycle on this one. So main thing is first I calculate this reaction by silver plus to neutral in a vacuum, and these two reactions in the solvent by take this optimized geometry, add the solvent and calculate the SC and total energy. From the energy difference, we will get the solvation energy, and by substituting these two energy with the thermalization corrections, we will get the reduction potential in vacuum, and then we can calculate the reduction potential in water medium by maintaining this cycle. So these are all equations here. But this reduction potential is kind of absolute reduction potential of the reactions, but it's not that much. If we want to compare with the experimental results, we need to get the standard reduction potential. So what I did, I used this hydrogen standard reduction potential and took this standard reduction potential from the literature and calculate the all standard reduction potential of my species for the last equations.
Well, technically, if there is a question exactly like how the solvent affect, like I understand what you're doing, you're saying you don't want to include conformation due to the solvent, you want really just solution energy due to the energy change, electronic properties change. But I'm kind of thinking, would be maybe reasonable if you do, since we already have optimized structures in solvent, right? So now you just take optimized, same as you do in here, but you take optimized structures in solvent and recalculate it in vacuum.
Yeah, I did that actually.
And then take optimized in solvent, right? Subtract and see whether the trends are different.
Yeah, I did that. But they have, in quantitatively, they have a little bit difference, but trend-wise is showing that, yeah.
This is good because, again, reviewers, like, they might really, because it's very easy point to notice, right? Why you're doing it vacuum. If you're talking about that this guy is really used for biolabels in a real cell, so they should be in at least water solution or some high polar solutions anyway. So at least in supplemental materials, we need to make this comparison, and then you just say, well, qualitatively not a big difference.
Yeah, for comparing with solvation effect, what I did in these two cases, I suppose like for this one, I optimized this geometry in vacuum, and then solvent, I did single point calculations. In another calculation, I take this one as an initial geometry, and then add the solvent and re-optimize that one. So in that case, the trend is same. Quantitatively, it's a little bit,
but in this case, you kind of have you still subtract the energy of the without solvent with the geometry without solvent, right?
Yeah.
Subtract the case when you have both geometrical conformation and electronic level conformation due to the solvent present. What I'm saying, you really can depict these two things, make them different, right? Because if you take geometry exactly as in a solvent, then again, in both cases, top and bottom, you will have, I mean, top and bottom according to your scheme, you will have exactly the same geometry, and it's really just the salvation energy, but now your geometry is different comparing to vacuum.
In that case, we need to include actually thermal entropy corrections for maybe with because of geometry changes too. We need to.
But why? I mean, entropy correction should be in the first place as well when you optimize it in a vacuum, right? I guess it's pretty much the same idea. I mean,
yeah, that
if you include correction there, then it has to be included into the second case. Well, anyway, it looks like it's very quick to run this. Well,
yeah, I do have that information. I just need to do calculations.
As a first step, I mean, as a first, explanation, first backup kind of idea about solvent effect. Those data where you kind of taking now both geometry change and electronic level change. So this is definitely has to be in the supplemental materials, right? And maybe I would say shoot these other calculations with geometry as in solvent, right? Even if you calculate it in vacuum, and see whether the trend is not really changing. And if not, then we're really safe for any kind of complaints about, oh, you don't include solvent, why you're not optimizing the geometry in solvent.
Okay, yeah, I'll include that in.
I have a question. So how did you actually do the solvation? Like, so right now you have the silver cluster, right? And then in the first coordination sphere you have some ligands.
No. It's
PCM. I use the CPCM.
Not direct.
Yeah, it's not direct. It's considered as a dipole. What's it called?
Continuum medium.
Continuum medium. Yeah, it's not a real solvent. It's like same dipole substance in the calculations here. It's not an implicit water molecules.
But his question is making sense, especially in your case, because you already see the formation of H bonds, right? In water, they also will create H bonds, and using the solvent just as polar media, right? How we call it? Right, but it's the same idea as you just have a mean field approximation. It's definitely not accurate because you will have formation of these H bonds, which might change everything, or might not. Yeah. So you're right. We probably should to put solvent realistically,
Yes,
but
yeah.
then it would be too much to calculate because yeah, definitely one layer would be not enough, right? And don't forget, although the systems look small, but it's heavy elements with completely filled d orbital, so it's a huge number of electrons. So that's why they're not very quick.
Yeah,
to calculate.
I read the one paper. They did not this system. They did the similar solvation effect on the iron system, ferric and ferrous and ferric ion, by using implicitly, different number of water molecules here. They tried to figure out how the solvation changed their reaction potential calculations. And they found that yeah, it changed the quantitatively, but if you want to compare comparisons between the like similar system with the similar number of water molecule, in that case you can compare the result actually. You don't need to do the explicitly the similar huge number of water molecules.
Oh, but they do iron complex.
They do iron, not they do just iron hydroxide, I guess. Maybe, and
But
then
it's a
put the-
complex. It's not.
small.
It's not
a
really
big
a
one, yeah.
whatever.
It's not that kind of
not
big
the
system,
iron
yeah.
particle. It's,
Iron particle,
it's,
yeah.
it's a cluster. Okay. I mean,
Cluster,
it's not a
yeah.
cluster. It's a molecule.
Molecule type things. So they try to figure out because how that.
But they also, what's the ligands? So the ligands can create these hydrogen bonds as well.
I mean here
No, in this paper which you refer to.
in that paper they try to figure out they form hydrogen bonds like water sphere by putting more
No,
water. here.
water is doing hydrogen bond with ligands on a complex, right? Because in your case,
I don't remember exactly that
in your
one, but
case,
yeah.
you can really have not just hydrogen bonds for water. You have a hydrogen bond between water molecules and the
Between,
ligands on the surface with your DNA basis, right?
yeah,
But
that's
but,
an interesting. Yeah,
but this is kind of again the thing which might be we might expect when the paper will be ready. One of the reviewers or maybe all of them might be noticed and ask the question. So at least referring to this paper
you know,
probably will reduce
that's something. Yeah.
very negative kind of response right away, and then they will be, even if they ask, they probably will ask it in a very mild, much more milder kind of tone, rather than oh this is a crap because you're not including the hydrogen bonds.
Yeah, so mainly we are actually focusing on comparative result between silver structure. So if you follow the, I guess, the same methodology, then we can get some comparative idea between the how structural difference and oxidation potential difference and going. So this is the main result. They have a lot of lines, so I'm gonna explain one by one for the first one. And for the top plane, this is the precipitated system with the cytosine and silver system from the 4 to 6. And for the black line is the oxidation potential for one plus to 0, not oxidation, sorry, reduction potential from +1 to 0. And dotted means is the odd number, and solid line means even number. I put the odd and even is separately because silver has a alternative effect of with the number of silver sizes because the spin is changing doublet to singlet.
Yeah, so your even number particles with positive charge behave similarly to the non-even number particles with neutral charge.
Yeah.
And back.
And vice versa. So important output, if you look in here, and also another two is a red one. Red one is a reduction potential from the +2 to 0. I consider the three different reduction reactions. So from the +1 to 0, 0 to -1.
Maybe you can write it on the whiteboard if you don't, or maybe you have these equations.
I have questions on the paper. Oh, you have the. So look like this one is that this reduction is the +1 taking on 1 electrons going to the neutral case. So I consider the three different reaction oxidation from starting at +1 to neutral, +2 to +1, and neutral to -1. So for easiest patterns, and the change of this system in the parentheses is changing from 0 to -1, +2 neutral, and +2 to +1. So it's given And when is changing in odd number, odd number is a neutral cluster, that's a doublet spin configurations. Similar as a even number is a +1 is a doublet one. So that's why they are they are the same line. So if you look at here, this is the even number, odd number one, and there's the solid, and for the singlet is changing from doublet to singlet in the even number. So just these three lines with the size, increasing the size, initially is increasing, and other one is overall is kind of decreasing. And they have one exceptional number that's actually, I don't have explanation for 10th cluster on this point. If we excluded this point, the same trend is saying that when your cluster size is increasing, the difference between the changing reaction potential for doublet to singlet and singlet to doublet is going to decrease, and it's going to smaller and smaller, the difference. So in many cases, if you look on the literature, they reported that in the larger size, like higher than 30 or 40 atom size silver cluster, they have a very, they don't have that significant doublet alternative effect. They have showing the similar one number of reduction potential. So, but when your cluster size is smaller than 10, it's important to see that specifically what is the spin configuration. And dependence on the spin is giving us a higher and lower reduction potentials. And another thing is, this is reported as a reduction potential. This is a negative number, so that means is that this cluster is this reaction is oxidation reaction in this case is more favorable. In this case, reduction reaction is more favorable in compared to this one. And
again, your dashed lines corresponds to going from doublet to singlet, and solid lines from singlet to doublet? Or not?
Not always.
Oh, it depends on the charge.
It depends on the charge, yes. Solid line is for even number cluster, and dashed line is for odd number cluster. Yeah. And just for easiest, these three lines, they are changing from singlet to doublet. And these three line is geometry is spin changing from singlet to doublet. Sorry, doublet to singlet. Yeah.
Top ones from doublet to singlet, and
Doublet
bottom ones from singlet to
singlet. Yeah. And this is the higher negative number. That means actually reduction oxidation potential is higher for those systems. So is more preferential to change the conformations from the doublet to singlet in this case. Yeah. In other words, yeah.
So again, it's easy to go from doublet to singlet, but harder to go backwards from singlet to doublet.
Backward, yeah. And this one is for calculation from the Bayer cluster. So in overall, except this line, it's also showing the same trend. Is the same difference is much higher in this here and is going on similar cases, but it didn't follow the same trend as this line. This line is going up, so all the difference is this one. But main conclusion is when you're going to very high larger sizes cluster, the difference of these two is going smaller, and for this one, with the increasing the size, okay, that should be more understandable in the next field.
I have a question.
Yeah.
So I guess you have two systems, right? One is clusters with even number of atoms. The other one is clusters with odd number of atoms. So why you separate them into different groups?
As I said, I separated because in suppose odd number and even number, they have a different multiplicity, the spin multiplicity, and they're showing the alternative effect in the silver cluster. Alternative effect means if you look at here, suppose like just compare the black line, only black dash and solid line.
Because if you put them together, they will be doing like this.
If I put this one, is changing, is decreasing and then increasing and decreasing and then increasing. So it's better to consider the separately spin with based on spin. So now you can give you will get a clear idea about how it's changing. Otherwise, you will see that it's just up and down, up and down.
Because you clearly see that your doublets,
Yeah.
I mean doublet to singlet and singlet to doublet definitely split it into two different groups. So that's why they behave, their overall behavior and relative energy is also different. And the bottom one is no ligands, right? No,
Yeah,
ligands.
it's a pure cluster.
And can you, I mean, for me, I don't remember, we talked about it long ago, but now it looks a little bit confusing. Like, what, can you summarize what exactly is the effect of ligand, if you just look on the effect of ligand, on whatever the category you go from, even, or single to doublet, or any kind of trends?
In effect of ligands, I would say, for the quantity purpose, quantitatively, for if you look on the number, effect by adding the ligands is decreasing the reduction potential. Decreasing. It's realizable.
Either doublet to singlet or singlet to doublet. For
In
both
overall
cases.
cases, in all cases, is decreasing the number. I have a table in the assay information, so you can compare. It's because when you put the layer of ligands surrounding, so it's very hard to take in electrons or losing any electrons. So that's why reduction potential is increasing. So it's very hard to go an electron chain move from the cluster to outside. So that would be my idea. Because that electron is reducing from the core, not the passivation side. Only from
the base.
From the base. So, and that base one is passivated by the ligands, so it's supposed to be, potential should be increased here. So if I say the reduction potential, this is easy to reduce than silver, than passivated silver. Oxidation, this one is easy to oxidize than this one.
Okay. And reduce means we're creating the.
We are taking off one. We are creating the plus charge, silver plus.
So again, the bare ones easy to create positively charging systems, and for the negated one, you're saying it's easy to create negatively charged
Yeah,
systems?
from the number, from the absolute reaction potential, yeah, it is.
So it's easy to create, let's say, from +2 to create +1. If they're negated, then it's easy. Rather than when it's a bare, then it will be preferring to go from +1 to +2 rather than +2 to +1. Right?
You need more energy, yeah.
Or going from 0 to minus is easy for negated ones. Oxidation, right? You're reducing the
0 to -1 compared to here in the. In even cases or odd number cases. That's another fact, because it's actually the number is 2, so 2 is here. So this one is higher, but not this one here.
Okay, so again, this,
So they have
this
a-
paper is very, I mean, this figure is kind of, especially the bottom one, if you compare top and bottom, becoming, the trends are not so easy to follow.
Easy to, yeah, you
So
need to
think
follow
about
a
how
different
you can read, like, then your writing has to be very clear, right? So all ideas, like comparing this with that, comparing this with
Yeah.
that, comparing that with that.
So it's very hard to actually conclude this one by one sentence, so you need to compare all
So it will
different
take, it will
factors.
take you some writing for
For this big figure, yeah.
to really make it clear in your discussion, right? Because the top one, I think it's easy to understand what's going on.
This one
For
is
the
not.
bottom, it's really very mixed, and
Yeah,
it's kind of very hard to compare with the top one. in the
It's
sense
because
of
it's because of
behavior.
because of this line, this red line. This reduction potential in this case is matched with this one is nicely. We can divide the two sides, but it's going up, so that's why it look like very much.
So the blue one is really kind of a strange
It's
behaving guy.
It's supposed to be here.
Uh-huh.
I mean, if you then you will get a similar trend.
And repeat again, what is your blue?
Blue one. Blue one is from the negative charge actually.
Ah.
Negative is from going from 0 to -1.
But then, if we can trust your data, then we clearly show, it's clearly showing that 0 to to negative for the negated one, well, it's probably kind of what you're trying to say, oxidation is easy, reduction is backward.
From the experimental point of view, it makes sense because this reduction potential is extremely low compared to all other.
So
Is
for
because-
where it's easy to go from 0 to -1, right?
No, it's opposite.
Oh, it's harder
Yeah.
because of the.
This potential for 0 to -1 and is the lowest number here, lowest potential reaction potential. So that means it's easy to go
No,
minus
what
to
do you mean
0.
most? There you have -4, I think, right?
It's -2 here. This one is
-3 something, right?
this one is -3 here.
So -3 is lower than -2.
Oh, you're comparing this one? I mean, I'm comparing this line with all other line.
No, I want to compare just blue because red and black qualitatively not very different, and the dashed one I just hardly see them, so that's why I just ignore them. But I want to see them. But blue one is definitely behaving completely oppositely, right? It's not just pushing down. It's also like where you have maximum, here you have almost minimum, right? Where it goes down, it goes up. So it's
Yeah.
almost reverse behavior with the size
Yeah.
and overall, as you said, like it's really going below these dash lines while these guys kind of do not. So that's why let's compare just blue, solid blue on the top and bottom. And you're saying that this corresponds to 0 to minus, right?
Blue
one is from 0 to minus one.
0 to minus, yeah.
And so which one again more easy, or how say, is there oxidation potential or reduction, whatever you're using? Is it reduction or oxidation potential?
All are reduction.
Reduction.
Yeah,
okay.
that's why, because experimentally always they present the reduction.
So
So I combine
overall, the value for the blue top is high. Is having the how say is more negative, right?
Mm-hmm. At least in up to 5. Yeah. Another one is around 2. Yeah, it's comparable to this point is comparable to this number.
And
So in this one, and another point is this line is look pretty odd because of, I guess, on the last point silver 10. So it's maybe because silver 10 structure, when we started with this reported one, silver 10 is a pyramidal shape. So they have inside, I mean, core electrons, I mean that shape, and volume is more smaller. Sorry, surface is smaller in compared to all other surface ratio. Maybe because of that is giving us a very different result. Because that structure is, in all other less than 4 to 9, all silver atoms on the surface, they have no core atoms. But in silver 10 is a pyramidal shape, they have a silver in the center and all the silver on the surface. So that surface atom ratio is not that much high compared to all of them. So that's why it's maybe because of changing this very different result in this case.
let's go first.
And I won't build that number also another thing because in synthetic, in experimentally, they synthesize by adding the silver plus 1 by 1. But I started with the whole big cluster. So that's why maybe different result in this case. So this is the only reduction potential for half reaction. Half reaction means just silver taking electrons and going. But if you compare the overall reactions, we wanted to look on overall reactions. Also is important. And I just put some reference paper here. There are a lot of difference. One saying that like oxidation, bleaching can be happened by increasing the oxidation of the silver cluster. Another one they're saying that is synthesizing cluster is growing by oxidation reactions. Silver plus is giving us electron and then form a cluster. These kind of things. That's the last one. This one. So it's important to know the overall reaction. So that's why I just consider the 2 overall reactions as model reactions. If you look at here, suppose like if we think that they form as whole system as a silver neutral cluster, and then by oxidation, by redox reaction, it form a silver plus and silver minus, suppose like these reactions, and then I calculate the redox potential. This is not reduction, this is redox potential.
So this is your net potential, or it's
yeah, net
it's
potential.
a net potential. Both come in like when you add both reduction
Oxidation, yeah.
oxidation and reduction
Yeah,
together.
it's a sum of both half reaction, I mean redox reaction here.
So it's a
Redox
potential.
potential, yeah. It's not an only reaction. And another reaction I considered, if we consider that suppose you forming a silver plus ion, and with the time with the redox reactions, you're supposed to have maybe silver 2 plus and silver neutral. In both cases, if you look on the number based on my reduction potential calculations, and this number is higher in this case, and this in the 4, 5, 6, and with the increase in the number, it's decreasing the redox potential from here to here. That may, and for if we're going to 1 by 1, suppose like 4, this is the negative redox potential, so this reaction is not a favorable. I mean, not most that probable.
Thermodynamically.
Thermodynamically, that reaction is thermodynamically more favorable. So we can expect that if we initial cluster is like silver plus, silver 4 plus, and then eventually you will get the more silver 2 plus and silver neutral. But if you consider the overall thing, suppose like initial is silver plus, and then you are getting the equal number of silver 2 plus, and you have some unreacted silver plus, ultimately you will get more number of silver, I mean, positive cationic charge cluster in your system. That's also experimentally true that everyone is equal, that you will get a cationic system, not a neutral system. And but that potential, that overall potential is 1.73, 1.9 and increasing, and with the increasing size is going down, going smaller and smaller here. Here.
Oh, this is significant. I don't know. 1.78 to 1. What? 1.03.
1.03. I guess it's significant. It's bold, so it's like around 50% changes. But also size is not that much increasing, but 6 to 10 only. And this is getting a very, I got a similar to the report, a synthetic experimental report. One says that this reduction potential, redox potential is decreasing with increasing the cluster size. If you, on one experimental paper, they synthesized 0.33 nanometer sizes and with a 3 nanometer size, and they compared the two reaction potentials. They're saying that this reduction potential is going to decrease with increasing size. And also it's showing the same similar trend that is going to decrease with increasing the cluster size. And so if we are going to synthesize the smaller cluster, it's always easy to get the cationic cluster everywhere. And the ratio of the, since this is smaller size, the ratio of the cation, oxidation state and the silver cluster size is higher in this case. Because suppose like if I got 6 and if it's produced a 2 plus, it's almost 33%, the ratio. And there is some paper, one paper is saying that it's also probable to get 6 to 10 oxidation state and cluster size ratio, especially in the smaller cluster. So this is kind of computationally proved, and also it's giving us a one feels like that our method is working pretty good to get an idea, overall idea about how the cluster size and oxidation potential is changing. So all of these things important because we need to figure out our cluster oxidation number, because our absorption properties also change with this with the oxidation number. Structure also change the oxidation number. So just for example here, I'm just showing you the two different of the most stable. Take it from the previous result. If I take the silver 6 plus and silver 2 plus, is giving us a very significant number here, changes here in the, and another thing is for the first one is the silver plus and silver 5 plus, 1 plus and neutral one. 5 is a double spin multiplicity and another 5, 1 plus 1 is a single spin multiplicity. So in those cases, if you go to the higher energy range, like 3.5 or higher than 3.5, is giving you the almost similar absorption feature. But due to the changing of spin, you always lose the lowest energy one. This peak, this transition is kind of result of the double spin multiplicity. And next one is can be tuned by changing the size and cluster size. And in that field, you'll see here, it's increasing the intensity here, 2 plus because. But in the other one, and the highest energy peak is going to be dark in this case. And we don't have actually exact answer of this one, why is intensity is going down significantly, the highest number one. But in the lowest energy peak and lowest energy one, we always getting the higher intensity if we go to the higher oxidation state, like this one, and you will get a more number of singlet spin configuration. That's why you will lose the very lowest energy peak. That's the main conclusions from the absorption properties of this one. And I guess this is all for this reaction potential discussion here.
Well, it's kind of strange that you show in neutral and +1 on the top panel with 6 atoms, right? With 5 atoms, and then neutral and +2 for the 6. You probably
that's
really
what I'm showing from here, because if you consider here, suppose like if 5 is showing that overall redox potential is positive in for these reactions, so we consider that it's more probable to get the silver plus and neutral cluster. Because if it's from the neutral cluster, and you're supposed to get the.
No, I mean I understand,
Yeah,
but still, even if we say this is more probable, right? I think for consistency, if you go back to your slide, I would probably show both silver 5. You're not showing all 10 of them, right? You just show silver 5 neutral, silver 5 +1, silver 5 +2.
Okay, I do have
Even if
that
you do have. I'm sorry, I thought you didn't.
Actually, I put this paper in the supplement as information. So,
Oh, okay, good.
and I guess
I mean,
I
just
can
for
make it
curiosity, it
bigger.
looks like why you don't show +2 for silver 5, even if you're saying that it's probably less probable to have it, it's still kind of interesting thing. Like, does it have the same significant effect on the spectrum?
Yeah.
So does it?
Yeah,
Too many lines now.
in 2 plus is always increase the intensity of the second lowest peak.
Oh, you also have in -1 here.
Yeah,
I see.
the blue color is a -1 and green one is 2 plus. If you look at here, this 2 plus is increasing the intensity here, and although there's a doublet one, and same as here, if you consider the neutral and the 2 plus is increasing this intensity in the second absorption peak. And due to the changing the spin, is losing this peak, another 2, but it is still here because of this spin, double spin.
I would suggest, since this paper, I mean, this figure looks like if it goes to the supplemental, I would suggest to add also the Low's transitions, just to see how because
Where the
I don't know, the green looks like you probably don't have any Low's transition, or maybe you do.
No, green the lowest transition is around here, and this is the.
Yeah, but it's not so obvious, right? For you, it is. Here it's really hard, especially like on the top one, you have some bump there, which looks like you have a green a little bit there, right?
Yeah, it is because of double
Right.
spin.
But it's hard to see, is it really a bump or it's just, I don't know, something. So probably if you
Yeah.
show the lowest transition, just either by arrow, so you can print the oscillator. Actually, you can use oscillator strengths on your on the other side of your axis, right? And show actual size, actual oscillator strengths. And just see, like,
Just
not
one.
all peaks, but just one peak, the lowest one, right?
Okay.
So would be since it's supplemental, just to be sure where the low state is and how bright is it. Well, obviously, looks like they probably will be not very bright for most of these cases, but this information would be useful.
Yeah. So that's the main effect. So you can try to explain. You can explain the absorption feature by considering their reduction potential, and you will get some idea about what would be your most probable cluster size and oxidation number, and that will determine your photophysical properties in this case. So I hope that these calculations would help give some idea about their system, the experiment still.
But am I right? So for your 5 case, you have this 2 plus charge, right? And your lowest transition is increasing significantly.
In the 2 plus?
No?
No.
Oh, no, not 2 plus, -1. The blue one, sorry. The blue one is -1, right?
Yeah. But
is it the like looks like your first big peak? Is it kind of where your lowest transitions are, or you have some ones redshifted?
Lowest one is not completely dark. That's true. Like all other, I mean, in doublet cases, they are
And can we
completely
see
dark.
that at negative charge, your silver 5 really increasing the slowest transition intensity?
Yeah, it's increasing
Yes.
like this here. But we don't consider this one is almost certain from the literature, and our calculation is very hard to get the negative cluster in there. And also from the synthetic point of perspective, because all cluster is synthesized by using the sodium, silver borohydride, something like that. So they have a silver plus always. Yeah.
But also, if you look on the +2, the green line, right?
Mhm.
Again, in a 5 case. So, but here it's doublet, right? +2 is doublet in
Mhm.
5.
So +2 is doublet and increasing the intensity significantly in the both cases. Yeah.
Yeah, but you still have a lowest bump, which is not very
Yeah,
very clear.
that's because of doublet spin. But in the second peak, that's also actually our main focus on all other calculations. For second peak is a charge transfer from is mixture of DD charge transfer and ligand to metal to ligand charge transfer. So in that transition is increasing due to increasing the cluster charges.
That's it?
Yeah, that's it.
This is your last play?
Mhm.
Oh, thank you, Jasmine. Any additional questions to the discussions which we had on the fly? Especially for those who never asked.
How are you?
I'm pretty good now. Please.
This is not counted. Try again.
Which bases did you use?
I actually don't know.
I use
Did you use?
Lenal 2DZ for silver and 631 GSTAR base for all other.
I guess I had a question when you were talking about your the reduction potentials. How come they were flipped? Like on the I think on the evens during the reduction they're negative, and then for the odd numbers they were positive. Why do we observe that trend? I don't know if you explained that, but I probably just didn't hear it. The fifth slide?
You mean here?
No, the next one.
The table, right?
Yes, the one with the table.
It's pretty much the same data, probably. It's easy to look on the table rather than on the figure.
Yeah.
This is the actually previous table you saw. There's a half reaction reaction potential is not overall reactions, just reduction potential of the half reaction reduction part. So this is I consider the full whole redox reaction, oxidation and reduction part, and then I sum up these two, and then get the redox potential of the overall. This part, this is the redox potential of whole reactions, not as a one. So, and these changes arising from the difference of the previous reaction here, because any changing from doublet to singlet and singlet to doublet is giving us two separate distinct reduction potential that leads to these changes.
Okay.
Did he explain or not?
Yeah. Understand it now.
Other questions?
I have a question that I do not understand even how to ask. Just
Try,
share.
yeah.
I will try to formulate to my best, and you try to share your opinions, but it is not well defined. So, the silver clusters do not form literal chemical bonds to your ligands. It is coordination bond. So, is there a chance to reproduce the same electronic properties, like spectrum, by removing ligands completely and tweaking the oxidation states, or maybe by putting some artificial ligand of much simpler nature, because this cytosines, biological things are mid-size, rather heavy, and maybe one can put maybe ammonia.
We
So
tried.
what is the
It was Naveen who was the.
so
No,
what is the
I
mechanic?
did
What
that too.
changes and
Yeah, it's because actually this, if you look at the absorption spectra, so these are the first two transition. I mean, second transition, especially here in this transition, and then later on, is not just a metal D to D transition. It's a
Actually, do you
transition
have
from.
orbitals or that
I
we
don't
use?
have. Yeah, I do have. I can show you from here. So this transition actually from the mixture of DD and ligand, D to ligand transitions. So ligand also playing an important role here in this case. So when I put the ammonia is very smaller size and is very highly what's it called?
And not
electron
conjugated.
donating things here. So it changed the adsorption property is giving a very redshifted transition for double cases. In seeing that it's
Especially if you
completely
don't have solvent.
blue shift, especially
With
yeah.
the solvent, it was not as dramatic shift, but still different.
Yeah, it's because of I guess ligand ammonia is very highly polar and then it's interact with the water. So in case of solvent, the effect is less than before. So
but do you still need this heterogeneous, complicated biological molecules with rings and oxygen and nitrogen? Can you do maybe nitrogen and then simple hydrocarbon chain? Just share more.
For modeling, you mean?
Yes, for modeling. For modeling, can you get reproduce the same electronic and optical properties with any simplification of ligands?
If you have a charge transfer state, then the answer is no. Because the orbital literally sits on this ligand, and any modification to ligand might be changing this property.
yeah, that's the one reason. There's another reason this because this ligand cytosine and guanine is not that simple ligand because they have especially guanine or they have more than two possible coordinate sites. Although I did not include that study, but it's also important which atom is coordinating with the silver. And also they have some other it's not just coordinating with one and all remaining part are inert.
Isn't it nitrogen? Only?
Yeah, they have two nitrogen. And also they have a one NH that also can form a hydrogen bond with the coordinate. Yeah. So it's not just like one part is active or other are
It
just
behaves
inert.
pretty
but
much in the
it's-
same way as in metal organic complexes.
Yeah.
Metal organic complexes, you also don't have actual bonds, right? You have a coordinated bond with a metal ion and whatever your ligand. And we know that any even slight changes to your ligand will change your ligand field strengths, splitting of d orbitals is different, everything becoming different. Right? Oh, it depends, of course. If your change on the ligands not very significant, then maybe it's not very different.
So for silver clusters, you cannot do things like you did in 2008.
Yeah,
Of
that-
those. You cannot
2008
split.
or-
You cannot split transitions on only core, like core of the nanostructure, only
Only
ligands
ligand.
and hybridized.
No,
All
we can
all
split it.
transitions are
all transition.
all low energy transitions are hybridized.
Yeah.
We can split it because some of them have less charge. Like on a three electron volts, this peak is usually kind of pure DD transition.
In the doublet cases, the lowest energy, the very dark one, this is the complete DD transitions. And this one is a mixture of DD and charge transfer.
But
And
I think
also, and
with
high energy,
right?
high energy also is more DD and they have some sort of, it's not completely pure DD.
Yeah, we probably cannot just split it, but explains the character maybe. Maybe not for this paper, but for the next paper where we're really talking about the effect on optical properties. Think about how can you introduce this DD character, PP, and so on.
Okay.
We need some maybe illustration,
So,
just
yeah.
split levels. I don't know.
I guess I did one calculation for DD or bit of population calculations in that you probably did one too. But it is pretty clear from the literature in our study that even our system also cannot give us a very realistic result because it doesn't have the phosphate chain is giving us more flexibility in the ligand, but real system is not that flexible as our. So if we include more complex system, it could produce a more realistic result.
But splitting into the kind of splitting your spectra for
this
kind of analysis, you probably can do, because what you can do, you can look on your Gaussian file with your energies, right? Energies, oscillator strengths, and so on. It also gives you the main contribution of ground state orbitals and whatever, kind of roughly speaking, the portion of HOMA to LUMA and so on, right? And then you can look just on the orbitals HOMA to LUMA and so on, right?
Which one,
And maybe even write a, I don't know how can we, maybe we can write a script or something. Well, anyway, so you can really probably differentiate the portion. Oh,
I guess
you can do projected dose kind of analysis
like
for the
that,
ground state, and then if you know which of the states contribute to specific, in which portion, to specific transition, you can really put the numbers, let's say 50% on DD, 40% on CT, from d orbital of silver to the whatever pi orbital of the DNA base, right? So probably this analysis can be done. This is not the main point, but for this other paper, where we really will be talking just about the spectra effect of all these things on the spectrum.
In that case, we need to talk about a specific, explain each transition, then get the orbital, which orbital is transit, and
I would say maybe
take the
not
population
each,
from the...
because you kind of have these main peaks, you probably can see like whatever we call peak number 1, peak number 2, and it varies a little bit in energy, but shape-wise you can probably split it into several peaks, and then just choose the most bright transition in each peak, and thinking that the other ones will be not very different in nature, right? So you can characterize a few, but from different ranges according to your maximum big, well-pronounced peaks in your spectra, and something like this. So you don't need to do for every. It would be too much work.
At least a bright peak.
Yeah,
bright
well, you start with the
transition
lowest one, and then maybe this kind of second peak, third peak, something like this. Brightest from the second, third peak, fourth peak, and so on.
That's
Right? Yeah, so this is probably will be very important issue, especially if we really talk about the effect on the spectrum. Anything else? Are we done?
Yes.
Yes. Done? Anything else?
You asked 2 questions.
It's one question. Either or. You have to choose one.
Anything else? Or are we done? Yes or no? Yes, there are more questions. No, we are not done.
Okay.
So, in many spectra, independent on the details of oxidation state and ligation and size of the clusters, you have a strong peak at around 3.5, a little above 3 electron volts. Where it comes from? What is the nature of this transition?
This transition is more a mixture of DD and charge transfer, but this transition is kind of conformations and ligand independent in the most of the cases. So it's almost always giving us a very high intensity always.
So it is D to D.
So this one is very much different if you look. So if you look at here, it's always high intensity.
And actually, I have a problem with your. Are you done with your question or not?
As you wish. I can keep asking. I can
No,
stop.
I mean, asking for the same question or a different question.
I didn't understood. I need more.
Okay.
Is it D to D transition or it is D to S? Which orbitals of silver are involved? Are they localized or delocalized?
Okay, I don't have that concept.
Is it possible to answer it this time?
Yep.
Through projected dose?
Mm-hmm.
No, you.
Or I
you
can
have
look on
this
the
information,
population
right?
calculation.
When
I mean
you
that-
calculate your NTOs,
But NTUs give us just overall shape, but it doesn't give us the nature of these D or S.
but
He's
you can
asking
just
specifically-
print population,
Yeah.
pop in your keyboards,
Mhm.
right? And then it can give you exactly what is your S contribution, what is
Yeah.
your PXYZ, PYZ, and so on,
Mhm.
right?
Most of the time, I assume that if we saw that it's going to silver, we assume that it's D.
It's
So that's
D
why
rather than DS.
yeah.
Okay.
Okay. Yeah, I'll look on that. Yeah.
Good. Thank you.
Because it's an ion, right? So you're losing your S.
But transitions happen from occupied to unoccupied. So
Yeah, but
when you ionize, you remove one of the d, one of the electrons from the orbital, and now this orbital becomes involved into optics.
But I don't think you have DS transitions there. It should be completely optically inactive. And this is again, you can just calculate based on quantum mechanics. From D and S orbitals of hydrogen atom and
It's not hydrogen atom. There is some
no, but roughly speaking, right? So you, of course, we will have some, but if it's optically inactive, you're not expecting that these transitions will be really optically active for the silver. Just because of the symmetry of your molecular
But
orbitals.
for hydrogen atom, DD transitions are not very active.
Well, for hydrogen, no. If you calculate DD transition, assuming that it's occupied, whatever you try to put on your hydrogen, just because of the symmetry, right? You will get this oscillator strength based on the symmetry reasons. Yes, oscillator selection. I think that's why we not really care about S. So it's all DD transitions which contribute to the optical spectrum, and not all. Some of them optically active, some of them still not optically active. Again, because of the symmetry alignment of your d orbitals, how they overlap. And this is a good exercise.
Yeah, they have a lot
And
of
I think
things. Yeah.
this was no one. You're not taking my physical chemistry course. When I was teaching physical chemistry course, so they do it in the homework. Not for DT transitions. They do it, I think, for. So they do SP, PP transitions and see what would be the standard strengths.
Oh.
I think SS, SP, PP, whatever your XYZ and so on. And calculating this, you clearly see kind of you support the selection rules based on this symmetry of orbitals in the hydrogen. So I have kind of a comment. Looks like for your bottom panel, right? So all your spectra go dying after 4.0. All your spectra going down, right?
It's maybe because of
Not enough states,
not enough study.
which means your spectra is not really realistic. It's not that it's really going down, right? We don't know. It's probably not enough space. So I would say I probably will not go beyond 4.0 for your figures
Or
to avoid this problem. Maybe even earlier than 4.0 before they really completely dying. Well, I mean 4.0 probably will be not so bad.
But yeah, but green one is not completely because lack of a transition because it's going down and
Well, it's a
going
green
up.
line, but the other ones really, I would say,
no.
I don't know. Looks like, are they really going down and then they will grow, or they just go down because you're not having enough states?
Yeah, I guess 4 would be fine. After 4.5 is lack of a state.
But then you also probably need to reduce it to 4.0 for your top panel as
Yeah.
well
Good.
to make it consistent. Done? Applaud?
I don't know.
Oh.
Enthusiastically. Good.
Other volunteers for next Friday?
Results? Discussion on results or what?
Mm-hmm. Would you be interested to maybe make a very brief overview of absorption?
Are we going to have group meeting with the surface chemistry group as well?
Yes, I will
Okay,
consider
so you
bringing
will
them as well.
think about how you can illustrate your
I'll try
structures,
to.
nanotube, and again, of course, we cannot show all
And it
structures.
doesn't need to be
So I need a
long
figure.
detailed. Not
How
as
many a figure for the front page?
Graphical.
Some-
Yeah, we can do it later. I mean, yeah.
Find
Separate
a way
thing, so I need
agree
different
with
figure for
idea
that.
to have a joint meeting. It take
figure one
time
and
to
the
Yeah.
convince that it is
Yes,
useful
that's
to
the figure, is actually figure.
Down
And
there.
two is a
They're
resolution.
Okay.
Because they put it really like this small size. It's only for abstract.
So no one wants to speak or make public announcements? for the group?
Right now?
Yeah.
No.
Okay, we are going off record.